All right. Hi, everyone. Welcome. In Lecture 2, DSCI 512, we're going to be talking about searching, different algorithms for searching. I have shown you snippets of code that do some kind of searching for us previously. However, here we go into the details and we'll discuss the time complexities of different search algorithms. And then I'll show you a couple of timing experiments with code in order to show you how the timings are like for different kinds of searching, different data structures. And then finally, we will talk about the concept of hash tables, hash functions, and lookup tables. And in this lecture, we find out what was going on with the sets that were so fast when we tried to search for items inside of the sets. Okay, let's get started. All right, so let's go back to the problem of finding whether an item is inside of a list or not. Here I have a function for you called search unsorted, which takes in some data, and then we give it a key, and then we basically want to find whether the key exists inside of the data. And data is just a list, and the key could be an integer that we're searching for. Okay. And then it returns just a Boolean value, true or false. We've seen this function, something like this before. And the code is pretty simple. For element in data, if element is equal to the key, then return true. Otherwise, it means that that key does not exist in data, so just return false. Pretty simple. Okay, so just to prove it to you that this code works, I have a number of assert statements. So here I'm looking for this key, 4, and then this is my list. And you can see in this case it exists inside of that list. 1,000 also exists, and 4 here exists as well. However, 2,000 here doesn't exist. And all of these assert statements should pass, because for those ones that I'm expecting false, here I'm negating that. So I shouldn't see any error, and that's hopefully what happens. So it passes all the tests. All right, so what is the time complexity of search unsorted? We've discussed this in the previous lecture. We just want to find whether an item exists in an unsorted list. Don't be afraid, say it out loud. All then, right, because it's unsorted, we don't have any prior information, so we have to go and look at each item to find whether that item exists or not. Okay, so all then, and in the worst case scenario, that item that we're looking for exists at the end of that list, so we have to go through each element. So that's the worst case. But if our list is sorted, we can do something more clever. In this case, there's an algorithm, very important algorithm called binary search. And the name comes from the fact that if a list is sorted and we're looking for a particular item, then we can consecutively find the middle element of that sorted list and then compare the key to that middle element. Okay, if it's larger than that, then we can split the list in half and throw the first half away, because we know the key is greater than the mid value. All right, so again we throw that first split away, and then we look at the next half, and then again we repeat the same thing. We find the middle value, compare the key to that. Is it greater or smaller? If it's smaller, for example in this case, we throw the second half away. And then we do this repetitively, so having the list in every step, splitting the list in half in every step until we find that element that we're looking for. So this is a very efficient algorithm because, again, in every step, we're getting rid of half of the data. So super fast. And the name comes from the fact that so binary means something that assumes only 2 values. And here it splits the list in half. That's why it's called a binary search. Okay. The caveat is, again, you have to, if the list is sorted, that's great. If the list is not sorted, then you have to sort it first to be able to do this, because if it's not sorted, you compare your key to the middle element. That doesn't give you any information, right? The key that you're looking for could be in the first half, in the second half. It doesn't give you any information. But if it's sorted, we know for sure that we're going to find that either in the first half or in the second half. Okay, let's take a look for take a look at the function for binary search. So here I have this function search sorted, and again it takes in the same arguments, the same data, and then we're looking for key. Now let's look at the algorithm. So while the length of the data is greater than 0, we'll start from somewhere. We find the middle element, the index of the middle element. Okay. If by chance that middle element is what we needed, then yeah, we stop the function right there. We stop the loop and the function right there. If data at the mid index is equal to key, okay, stop it. If not, which is usually the case, if key is smaller than that middle point element, then we can throw half of the data away. So in this case, for example, the key is smaller than the middle point, so I only need the first half of the data. This is why here I'm using this particular way of indexing. So everything up to the middle point. The rest is not important to me. Otherwise, take the other half, right? I'm throwing the first half away, and then I just look at the second half. Okay? Pretty simple, but very elegant, very, very efficient. Okay. Now, let's look at some data and some tests. Okay. This data, as you can see, is already sorted, so it's suitable for a binary search. And I have, again, a set of assert statements. So -12 here should exist in the data, should return true. And again, some other values that shouldn't exist in the data. And let's run this code. And just by running this code, it doesn't really give us any idea how efficient that was compared to the other one, because our lists are pretty small. It will be fast anyways. All right, so the important question, what is the time complexity of search sorted as a function of the length of the list? At this point, you probably know the answer to this. Maybe I've mentioned it in the lab or in the previous lecture, but can someone call it out? It's log n, but why? Exactly. Mm-hmm. Right, yeah. So the reason is that we're actually looking for the number of times that we can split the list, right? That would be the time complexity, because the other operations that I'm doing here, for example, computing this middle value, like looking at this condition here, or doing something like this, these are not, these are all just constant time operations. Okay, so they don't take these are not a function of n. So the only thing that's important for us is how many times are we going to split that data, okay? And the log function exactly gives us that. So, for example, whenever you say, let's say, log of, suppose that 8 and to the base of 2, what this log tells us is how many times do I have to divide 8 by 2 to get to 1? That's exactly what we're looking for in this binary search, right? So I have to divide this by 2 3 times, right? And then I'll get to 1. It means that there's only 3 steps that I have to do to decrease this down to 1. This is the entire number of steps. Suppose that this is n, and then this algorithm will be log of n, because that's as many times as we can split the list in half. Okay. Any questions about this? I don't know if you remember or not, in 511, I actually gave you a question in lab 1. I wanted to show you kind of give you a glimpse of the binary search. I gave you a question about finding roots of functions. I don't know if you remember that or not. So for roots of functions, suppose that we have a function like this, x, and here, and then the function crosses this at a point like that, and suppose that this is 1, this is 3, and we want to find the root of f(x) equals 0, okay? And in this case, I told you that it's very good if you use something like the bisection method, which you split the interval in half at every step, and you compare the value that you're getting compared to this middle value, and you throw this half away if it was larger than that, and you throw this half away if it was smaller than the mid value. So that was exactly binary search, but in a different context. And the reason that this worked was because the values of X are sorted, right, by default. Okay. All right. Well, O-log-N, we discussed that question. So what happens if you call search unsorted data? And what happens if you call search sorted on unsorted data? Okay, so what happens in the first scenario? Search unsorted on sorted data. Would that work? Yeah, because you're doing linear search. That would work like at whenever you want. It doesn't depend on whether the list is sorted or not. But in the other case, search sorted does not work on an unsorted list for the obvious reason that comparing the key to the middle value doesn't give us any information, basically. Okay. This is just an example. One exists in this list. However, search sorted gives us false because it doesn't work. Okay, interesting question here. Why doesn't the search sorted function start by verifying that the list is indeed sorted, and then do the log n kind of search? Exactly. So if you want to check whether the list is already sorted, you have to go through each element and compare each element to the next element or to the previous element. Then you're doing O and O of n operation. Then okay, in that case, just let's sort the list beforehand because it's not much more expensive. It's just n log n. So it doesn't really make any sense to check whether it's sorted or not. Okay, now before moving on to the next section, are there any questions so far? All right, so we're going to measure the running times with these four approaches. We have an in operator you can use it with any collection, with a set, with a list, with a dictionary. We also have our function search sorted here, which is our implementation of binary search. We also have the in operator, again, with a list, and search unsorted, which is our implementation of linear search. Okay, so in all of these cases, I'll look for element -1, and the reason is that I want to go through all of the elements. So I want the worst case scenario. So I'm generating numbers from 0 to 100, 1,000, 10,000. -1 obviously doesn't exist in there, so it has to go through all of the list, the entire list. Okay, and the code here is, there's a lot of comments for you. For example, the arguments for this timeit function, dash q just tells timeit to be quiet and not print anything to the output. O means that I want to save the result of this timing thing in this variable. And dash r also tells this timeit function to only do one run of the tests in order not to wait like for half an hour to do all of that. Okay, so in each case, here I'm doing search sorted, x key, and then appending the results to this, and then search unsorted in this case, search sorted in this case, key in set, and what is and this is the in operator for the list. Okay, unsorted, sorted, key in list, key in set. So let's run this. It's going to take a few seconds. Okay. And then I'm going to put the results into a pandas data frame just to have a look at them in the table format and see whether the results actually conform to our expectations or not. All right. Should be done soon. Okay, we're done. And I'm just putting everything inside the data frame over here. And just take a look at this data for a minute and see if the results actually are what you expected. good, or? Okay, let's discuss the results. So first case, in this column, so note that I'm increasing the size of the data set by a factor of 10 at each step. Unsorted list, linear. So the linear algorithm is just linear, O of n. So if I multiply the size of the data set by a factor of 10, I expect the running time to go up by a factor of 10. And here you kind of see that. Roughly this is, this multiplied by 10 gives that, multiplied by this gives this. And it's kind of really nicely shows that linear trend in increasing the time, the running time, right, for our linear search. And on this second column, we have unsorted list with the in operator. The in operator is a built-in Python operator. It's under the hood, I guess it's written in C. So it's way, 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 way faster. But we can still see for large numbers of the data set, we can see that linear trend again emerging for the last 3 rows. So here, this value is 10 times, roughly 10 times larger than this one. This one is roughly 10 times larger than the previous one. And for the smaller values, it's so fast that it's probably getting shadowed by the other operations that are going on my laptop, for example. Okay? All right, this is also interesting. Sorted list binary. So you can see that the runtime increases by almost a constant number of steps for each multiplication of the data set size by 10. And that is an immediate result of the log n operations. So if you have, for example, something like this, so suppose that instead of n, I have 2n. So in this case, log 2n will be actually equal to log 2 plus log n. And in this case, this is just 1 to the base of 2. And you can see that we've increased this, we've increased the data set by a factor of 2. We've doubled the size of the data set, but there was only one extra step that we had to do. So one more splitting, right? This is why it's so efficient. So if this number was much bigger, something else, for example, let's say 2000 log of 2048 n. So I'm increasing the size of the data set by this factor 2,000 times, right? And if I do the same kind of analysis, so 2 to the power of 11 or 10, would be that equal to 248? Oh, 11, okay. So it would be actually 11 plus log n. That's fantastic. With just 11 more steps, we can find the element that we like. The size of the data set is 2,000 times larger. That's why it's so efficient. And we kind of see that over here. You can see that, 3. One more step 4. Here we have 2 more steps, but who knows what's going on under the hood on my system. And then again, 1 more step, 2 more steps, 1 more step, roughly 1 step. Okay, the Python set, it doesn't matter what the data set size is. It's always something as small as something to the, like 10 to the power of minus 8. Okay. So questions about this table, these experiments? All right, so I've used Altair a couple of times in these notebooks. I'm not an expert or anything in Altair. I just barely know how to use it. I just used it because it gives the output in SVG format, which is vector, which is highly readable. But again, then I found that there's a way to do that in Matplotlib. So yeah, don't assume that I know much about Altair by doing this. Okay, so here I'm just plotting the results of our timing experiments here in this plot. And you can see that, so the Python set in is just constant. And then you can see that this sorted list binary, you can't really see the logarithmic curve because it's increasing so slowly. And you can also see that the searching within or the linear search, basically both of them become linear after a certain data set size. Okay. And all right, let's see what I have over here. Yeah, here I'm just comparing the binary search compared to the set n, and you can see clearly that the in operator for the set is just constant, and the binary search, although it's very efficient, it still takes some certain number of steps. Okay. All right, so next section is about sorting. Sorting is a classic topic in every algorithms and data structures course, so it's kind of necessary to cover it a little bit for 10 minutes here, although we won't implement the different algorithms for sorting because that takes a much longer time to do that in the classroom. We don't have that much time, but here we just look at how sorting is done with a couple of simpler algorithms, and then for the rest, I can point you to the references that discuss this in more detail. Okay. So for sorting, how can we sort an unsorted list so that we can use binary search? Binary search is very efficient. We want to do that, but we have to sort our data before doing that. Okay. So selection sort, I have actually shown you the code for selection sort in the previous lecture. You have seen this code before. So with selection sort, what we do is that we have a bunch of data. It's unsorted. We start from the first element, okay? And then we look at the entire data. We say, what is the minimum value in the data? Okay, the data is somewhere in the list. We swap the two, and then we move over one index. And then we do the same thing starting from the second index. What is the minimum value in the rest of the list? Because the first one is already sorted. We do this, and as we go through the list, everything to the left has been already sorted because we switch the places between the minimum value and the value that's already there. And at the end, this will result in a fully sorted list. Okay? And this is essentially what I'm doing here. So here, I say that look at anything between index I all the way to the end of the list and find the minimum value, the index of the minimum value. Okay, so we find that, all right. Now in the next step, we say that that's not the right place, so let's swap that. Let's bring this to the beginning of the list, and let's move over one position. Okay, and now do the same thing. We're happy about the left side of the list, and then let's do this to the rest of the list. Again, look at the entire list, find the minimum, swap the places, go to the next. Look at the rest of the list, find the minimum, swap the places. As you go through the list, it becomes sorted. But what is the problem with this algorithm? And somebody actually mentioned this in the previous lecture in terms of the time complexity. So what is the time complexity here? We are having a loop that has n iterations. Things look quite harmless here. Yeah, and it's n squared. And why? Exactly. That's the problem. So something is hidden behind that np.argmin, because we have to, in order to find the minimum in the rest of the list, I have to look through the entire section of the list to find that minimum. So that's linear time. You're doing that for every step. So linear multiplied by linear n squared. Let's run this, and we already discussed this. However, you might also tell me that, okay, when we're at the beginning of the list, we're doing more work. When we're at the end of the list, we're doing less work. So how is that still n squared? The thing is, in time complexity analysis, we don't care about constants. And, for example, this is similar to this situation. So if you have a square of edge size of n, what is the area? It's n squared, right? What is the area of this? n squared over 2, right? And both of these areas, the one is n squared, the other one is n squared over 2. Both of these scale with n squared. So it doesn't matter. In the beginning, we do more work. And as we get closer and closer to the end of the list, we do less work, but it doesn't matter. It's just a constant factor. It still scales with n. Okay. All right. Let's see what's coming next. So if you want like a more rigorous proof, this is intuitive. If we compute the total number of steps that we have to do this, computing this minimum, it's actually a arithmetic series that you can see here. So n steps and then n minus 1 steps, n minus 2 steps. And if you sum all of those steps up, you arrive at something like this that you can see over here. And again, we don't care about lower order terms, so n squared. Okay, interesting question here. Can we find a sorting algorithm that takes log n time? So someone comes to you and says that I invented a machine learning algorithm that sorts this list in log n time. Can you believe that person? Precisely, yeah. So the problem is, if you want to sort the elements, you have to look at each element at least once. So at least linear time, okay? So this would be a false statement. It's like the conservation of energy. You can't just spend some energy out of nothing. You have to borrow it from somewhere else and then use it for some other purpose. So here, the real answer is that we don't have a sorting algorithm that's faster than n log n. That's the fastest that we can get. And these algorithms that I have mentioned here, merge sort is one of the most famous ones, quick sort, and a bunch of others. They are all n log n. We won't go into the details of how these algorithms work because each one of these take maybe half a lecture, each one of those. So you're welcome to check out these links, and also you can talk to me if you want me to introduce you to other references, but we won't talk about these in detail in the class. I've also shown you a glimpse of merge sort in labs of 511, and I think all of those were optional questions. But if you have done that, I have also actually shown you how you can merge two sorted lists. So I don't know if you remember that or not. So the merge sort actually uses exactly the same kind of argument. So it breaks the list into separate elements, and then it works its way up. So it merges each two neighboring elements, and then you have larger and larger lists that are sorted, and then you merge, and then you merge, and then you merge, and then at the end you arrive at a completely sorted list. But you don't have to know that. So the only thing that's important is that merge sort is n log n, quick sort n log n, and when you do sorting in Python and NumPy, these are the algorithms that are used under the hood for sorting. Okay, with that, we're actually a bit, we went a bit faster. So take a break before the next topic? Yeah, I think that's a good idea. So let's take a break of 5 minutes and then come back. All right, we're back. Okay, let's see. Okay, so the whole story about the sets and dictionaries and why looking up inside of those data structures is very fast. So, okay. So as we have discussed so far, we have seen the results for sets in 2 lectures. Yes, they are so fast, but how is that possible? So before discussing that, I need to discuss a concept calling hash functions, which we have to go through before I discuss the rest of this topic about sets and what makes them super fast. So a hash function is a function that is a mapping between some data into some integers. Okay, and it's kind of similar to what you do, for example, with SSH keys. I think you've learned about those, right? Yeah, so SSH keys, you have a password or something about your computer, and then it converts it into just something looking very random, a string of values. This is similar, but instead of converting things to a string, it converts everything to a number, and we call that number a hash. Okay, and underneath this hash function is some function that people have defined in a particular way, and it basically looks at the data and deterministically generates some integer that might look random, but it's actually not random within the Python session that you're running. Every time you restart Python, you might see a different value, but within this session, that hash value will be the same. So it's a mapping between the data to some integer. Okay, that's all what it does. All right, so for example, here I'm hashing this string MDS, and randomly looking negative integer, and then empty space, the hash is 0, and hash 5.5, a float, or integer, a negative number, and something even like crazy like this, and also, okay, so you might have seen an error like this in 5.11. It says unhashable type list. So this is a very important point here. Some objects in Python are hashable, meaning that we can take them, pass them through a function, and that function generates a unique value for us. It's kind of an identifier of that object, if you will. So here, for mutable objects like a list, you can generate the hash. And the reason is that because the hash function is generated based on the entire data that's inside of that object, and the list is mutable, if it generates a hash for you, and later on you modify one of the elements inside of the list, then it's no longer working, right? So as soon as the data type is mutable, as soon as you can change it, then it cannot be hashed. So a list cannot be hashed, right? What is another data type that cannot be hashed? A dictionary, right? What about a tuple? You can hash it, right? Because you can't change it. A string, you can hash it because you can't index into it and change one of the characters, right? So that's the most important point about hashing different objects in Python. And this hash function, this implementation, is something that you can actually look up in Python documentation to see exactly how that number is generated. And it has to have some properties, which I will discuss later. Other than that, it'll be something that's up to the programmers and coders to how to implement this hash function. You can implement your own hash function. Okay. Let's see. So a tuple, yeah, I can hash that. Even I can hash none. And when we say that the Python set is a hash table, it means that the items inside of it should be hashable. And that's the reason that you can't put a list inside of a set. So let's just quickly show you what it is. So an empty set here at 5.5, okay, that's hashable. At MDS, that's hashable, all right. And that's our list, that's our set. And then at this, it says unhashable type list. And you have seen this error somewhere else as well. If you're trying to create a dictionary and for the keys, if you use a list for the key, it will give you the same error. It says unhashable. Okay. Again, this is possible because this is a tuple. Now, let's see what this hash table is when we discuss, when I set a Python set is a hash table. Okay, instead of reading through this, let me just say it verbally. Okay, so a list or an array in another language is basically just a set of data. And then for each data, we have an index associated with that, right? If you know the index, you can go and access that particular data. A hash table is a very, very similar data structure. You have a set of keys and a set of values. And a list could also be viewed that way. You have a set of keys, which are the indexes, right? A set of values, which are the data. And in a hash table, again, you have a set of keys and a set of values. However, the thing that makes it super fast is that the value itself gives you an idea about where that value could be found in the memory. That's the whole mystery of these set objects and these hash tables being super fast. Meaning that if you have some data inside of your set, you have a string MDS, you have a number 5.5, you have a number 1000. If you want to check whether 5.5 exists in that list, you hash it, you pass the hash to the hash table, and then basically it's like having the index in a magic way, right? You have the index, you just go and check if that exists there. That's it. It's a hash table. So as soon as the values are hashable, we can use this property. You can hash it, that gives you some index, okay? Some index because it's an integer, right? Gives you some index, so when you want to check whether it's there or not, just hash it, just pass it through that hash function. It gives you a hash. Pass it to the set. It either exists or not. You don't have to go through each element and check them. That's the concept of a hash table. Okay, so here, before that, any questions about hash tables? Okay. So again, the key takeaway, the main point about the hash table is that instead of just putting stuff into a list and indexing them like consecutively, list 0, 1, 2, 3, 4, you use the data itself to generate the index. And that index is just called a hash in this case. Yes, because a set is implemented as a hash table. I will also discuss that a dictionary is also implemented as a hash table. And here I have an implementation of a hash table myself, which is super slow. It's not something really ideal, but just to show you the idea of what a hash table data structure looks like, what the implementation looks like. Okay, so let's see what it is. So class hash table, and then I have some stuff, like some data in my hash table, obviously. And one thing here that's very important about hash tables is this concept of buckets. So we have buckets of data, and this is something that we have to decide in advance. So you've seen that some of those hash values were pretty large, right? And you might be asking, okay, if that maps to a memory address, I cannot give the entire memory to this particular set and say, okay, this is all empty, something is over there, okay? This is not efficient. So I have to basically do something to that hash so that I can put it neatly in a tight space so that I don't waste much space, okay? So in that case, okay, I specify I have this number of spaces, buckets or drawers that I can put stuff in. How do I put stuff in those buckets? Based on the hash value, okay? One of the most common methods of basically deciding where each element goes, which bucket it goes into, is by using the mod operator. Okay, how does this work? So suppose that we have 4 buckets, and we also have a hash value. So how are we going to decide where each element goes? Okay, what we can do in the simplest case, in the most common case, is that we divide the hash by the bucket size, by 4. We have 4 buckets. We divide that by 4. You get a remainder from that division, right? That remainder cannot be larger than 4, right? Okay, so that's a good idea here. So regardless of what the hash is, I will always get a number between 0 and I will always get a number between 0 and 3 in that case, right? Because if it's a 4, it adds 1 to the quotient. Okay, so I can use the mod. The result of this mod is always something between 0 and the quotient, or the number of buckets. Okay, so it gives us a nice way here to do this. Let me walk you through the code. Okay, so the way that I implement this is that I have a set of stuff, and then I have a number of buckets which I have to decide. And then I'm going to say each bucket is represented by a list. Okay, it's just a container. All right, so for I in range of num buckets, append empty lists. Okay, now I have to now do the important stuff. How do I add stuff to the to my buckets? So if okay, so just disregard this. Here we say the self stuff, and here is deciding where the item goes. We say hash that item, hash that data point, divided by that number of buckets, take the remainder, and use it as the index. Okay, and then this is the index location, right? And then we go into stuff. That gives us one of the buckets, and then we append the item to that. Okay, and then how about when we want to do a lookup in that hash table? Again, similarly, because we know that that hash item kind of gives us an idea of where that item is, then we can just hash it, mod it with the number of containers, stick it right into this stuff, this container kind of thing, and that will tell you whether that item exists or not. Okay, so you don't have to do a linear search. That's the beauty of it. Let me just run this and show you a couple of examples before letting you ask questions. So here, HT, my hash table, printed, it just contains 4 buckets. Now let's add some stuff to it. Add hello. All right, it went into the last bucket because its hash, the remainder of its hash divided by 4 gave 3 in this case. Okay, hash hello. Yeah, the division of this number by 4 gives 3. This is why it went into the last container, the last bucket. Let's add more things. All right, goodbye went into this second bucket. Test went to this, also went into this second bucket. Huh. Okay, item also went into the 4th bucket. What went into the 1st bucket and blah. We're just testing whether this blah exists inside of the hash table. It says it doesn't. And if it was, it would have been in buckets, in this bucket here, this empty bucket. And then this contains works for item because it exists here. Okay. All right. So, do you worry about anything here in this implementation? Exactly. Right. So if we end up, we have only 4 buckets. So if we're adding a lot of stuff, we end up adding a lot of stuff to the same bucket. And the hash mod number of containers only tells us the index to the bucket. So we have to go into the bucket and still search for the item that we want to have. So if a hash table gets loaded very harshly in each bucket, in each location, then it defeats the whole purpose of the hash table. All right, so here's why this hash function is implemented in Python. Because it has to be implemented in a way that it gives like a nice uniform distribution of hash values for you, so that this phenomenon doesn't occur. This is called collision. So when you put stuff into the same bucket, this is called a collision of items inside of that. And this is something that we usually want to avoid. If we are able to limit the size of items in each bucket, suppose that we have, let's say, 10 items in each bucket, max, then we can guarantee that our algorithm will still be O of 1, constant time, for lookup, right? Okay, so how can we do that? Question 3 on the lab actually addresses this issue, which I will discuss. Yes? Yeah, if within each bucket, you have to do the linear search within each bucket, right? Yeah, that's a good question. How come the overall search time complexity is O of 1? It's not. If you have a lot of collisions, it's not. That's the problem. So we have to have a strategy to increase the size of the hash table every once in a while. And this is on question 3. So on question 3, you generate sets or dictionaries of different sizes, okay? And you have to consider all of the sizes, not just discrete values, not just 10, 100. You have to start from 0, 1, 2, 3, 4, 5, all the way up to, let's say, 10,000. And you will see that what Python does is something like a step function, like this. So every once in a while, it increases the size of that hash table. What's the problem with that? Yes? What the size of the dictionary? That's true, but what about time complexity, not space complexity? Two. Exactly, that's the thing. So every time that you increase the size of that hash table, you increase the size of the buckets, you change that remainder thing that we were doing. So you have to basically reorder everything. Okay, so you have to copy things over. That's all of that. Okay. Oh no, okay. This problem again. So the thing is, if you do that very rarely, that's still okay. Okay? And in that case, if for each, for example, 1,000, 1 million additions of items, you do just one increase of size just once, that's O of n, that's fine. Because when you average that out over n additions or n items, that's still a constant. O of n for copying, and then you have O of n total operations, that's still O of 1 in total. So it averages out. This is called a concept called, so if you want to say what is the time complexity, you say that it's an amortized O of 1, meaning that every once in a while we are doing some work, we're distributing it over so many steps that it doesn't concern us that much. So that's demystifying what this hash table is doing under the hood and why is it so efficient and the issues with increasing its size. Okay, let's see what I have here. All right, so before moving into the next section, questions about this? Yes? That's exactly true. So there's a concept called the load factor. So we say that, okay, the total number of items in that bucket compared to the total number of items in that hash table should be some factor that we want to keep it small. If that's the case, or if you keep it constant, you can guarantee that, then yeah, it's constant. Yeah. Any other questions? Okay. All right. So this was this idea of hash table is directly implemented as the concept of a set in Python, but we also have another data structure that you've used a lot, which we all like to use, which is a Python dictionary. This is, again, a hash table. The only difference is that instead of having just the data point, that particular data that you hash, you also have some value associated with that. Okay, so a key and value. So you hash the keys, you store it in a hash table, so whenever you want to find that item by the key, it's super fast. You go to the key, you read the data. Okay, so a dictionary is, again, just a hash table. The only difference is that there is a key, which we're looking for, and associated with that, there is some values. That's the only difference. Just a variation, a slight variation of the idea of a bare-bone hash table. Okay, and let's define these. So you can see that I can create a key 5 because that's hashable. String the character B, it's hashable. 5 in D is an operation of constant time because I'm looking for key. 5 in D, okay, 9 in D. It only searches the keys. So 9 in D, although we have that as a value, it says false because it only looks at the keys, okay? So D5, yeah, we have a value there, and this value is not there, okay? When it hashes it, it looks at the corresponding bucket, it doesn't find it, all right. And then again, we have that problem. The keys should be hashable. So it says list is unhashable. We can store that list as the data or as the value for that hash. It's okay, but not as a key. Okay, let's see what I'm doing here. Key value F items, just printing stuff. Okay, so we can have nested dictionaries, and we have a question in the lab, question 4, that you have a dictionary of dictionaries. That's quite fine. As the values, you can have dictionaries, but you can't have that as a key. Okay, so we have, around 15, 20 minutes left. I want to discuss one closely related topic of default dictionaries in Python, which makes your life easier for the last lab question. But before that, are there any questions? Just randomly asking. Okay. All right. Okay. So the default dict data type, I think I mentioned this in the lab somewhere, that if you want your implementation to work more straightforward, you can use this default dict. You can do it without this, but this makes your life easier. So suppose that we have an example over here. I want to obtain the multiples of 5 in a range of numbers between 0 to 100. So whenever the remainder is equal to 0, meaning that it's a multiple of 5, just append it to that list, and it works. Okay. So now, let's say I want to compute multiples of 2. Okay, works. Multiples of 3, same idea, works. Multiples of 4, same idea, works. How about if I want to compute the multiples of several numbers, 100 numbers, in a range of 0 to 1,000? I cannot repeat this whole thing over and over again. So one way that we can do this is to use a dictionary and use each number as a key, and then its multiples as values. That's a reasonable way to do this. So in my dictionary, suppose that I have 2 as the key, and then I have a list that says, okay, these numbers are its multiples in this range. And then 3, these numbers are its multiples in this range. 5, these are its multiples in this range. Okay, let's see how I can do that. All right, so I define multiples of as a empty dictionary. And I say for base number in 2 to 10, so these numbers, I want to find their multiples within this range. Okay? Just to be more efficient, I've coded it differently so that I don't copy my code around and compute that and store it in a different list. So let's do this. All right, error. So what is this error? For base number, do this. If the base number mod this is 0, add this number as a key, okay, and append that number, which is a multiple, to that as a list. What's happening? Exactly. The key doesn't exist, and that's why the dot append wouldn't work, because we want it to be a list, but we haven't defined it yet. Okay, how can we remedy that problem? We can do something like this. Okay, same code, everything is the same, but before doing that thing, first create that list inside of for that key, just an empty list, and then you can append. And you have encountered this problem in labs of 511 where you had to initialize the values inside of a dictionary in order to be able to append to them. Okay. And this is basically the idea of a default dictionary. So these are the multiples, okay, it works fine, but if we use a default dictionary, it makes our life easier because it has a default data structure that we can assign to it whenever a key doesn't exist. So let's see. I'm going to skip these two code cells because they're not that much important. So the way that we can use default dicts is to collect from collections, which is a built-in Python library, import default dict. Again, it's a data structure super similar to a dictionary. The only difference is that if we refer to a key that doesn't exist in the dictionary, by default it gives us something that we specify. So here I'm specifying, hey, give me a default dictionary which has a default data structure called list. So whenever you see that key, if it exists, it exists. If it doesn't, just return an empty data structure of that kind. And if you now look at this DD dictionary, you can see that a hello is added actually, which is super convenient, with an initialized with an empty list. That's the whole purpose of default dictionary. So you don't have to initialize those values. And now if I have a new key, I can, without initializing it, I can directly append to that, right? Because now, by default, it sets that new key as a key, and then it sets its value as a list, so I can directly append to that. That's the whole purpose. And now I can rewrite that code very much in very much simpler terms by creating a default dictionary, and instead of initializing that, I can just append. So it makes it much more easier, and in fewer lines of code that would be possible. Okay, let's see what else I have here. Yeah, DD. Okay, and you can also see that the DD is default dict. Yeah, and it is an instance, a subclass of the dictionary class. So basically just the same thing with more extra features. One last point that I want to discuss is that when using the default dictionary, be careful not to use it in this way. Okay, so if I do this, yeah. So it says first item has to be callable, so you have to supply the name of the function, not call it. So you pass it the name, and default dict by itself, it goes and call that function. So you shouldn't do this. Just remove the parentheses. Don't call the function. Just pass the name. Okay? And you can also, instead of just those constructors that we have in Python, like list or int or float, you can also use your own function to generate some values for you. For example, I'm defining this function over here, an anonymous function, which always returns the string. And if I refer to a key that doesn't exist, it gives that as the value. Okay. And then, see what I'm doing. Not too important. No, nope. Okay, initializing the default dictionary with integer gives us a value of 0 by default. So, for example, here I can directly call that dictionary and add numbers to it because I have initialized it with int. When that key exists, it exists. When it doesn't exist, it just gives you an integer of 0, so you can directly append to that. We had this problem in 5.11 that you created that inventory or store object that you wanted to add stuff to the inventory or to the stock, and you had to initialize the key values before that, and it helps you with that. Okay, any questions about default dictionaries? This will be very helpful for writing code for the fourth question of the lab, because you have to use dictionaries within dictionaries and compute the occurrences of certain characters. Yes? So as soon as you give it the int function, by default the int function returns 0. Oh yeah, you can do that as well. Yeah, absolutely. Okay, any other questions? There's another type of object that's pretty helpful, very similar to this one. I want to discuss that as well. Okay, not super important. You can still do your own dictionary thing, but this is something that's going to be very helpful. Okay, so there's this type of dictionary, another type of dictionary called a counter, which again you can use to your advantage. And it's basically, again, it's just a dictionary. However, whenever you define it, you can immediately start, basically start counting things with it. So here I say that whenever you find this character inside of my counter object, just add 1 to it. This is useful for finding occurrences of something. So instead of initializing it with 0 and then adding 1 to it, whenever you find that key, if it doesn't exist, add 1 to it, because by default, it gets 0. You can do the same thing with a default dictionary, but it's just syntactically it looks nicer because other people can immediately see you're using a counter object. All right, and it has some nice properties that you can, for example, do most common item and stuff like that with this counter object, which you can explore. I thought these will be helpful for your lab questions, and you might see this in codes written by other people. Okay, any questions? Well, actually, we have quite a bit of time left. So do you want to take a minute of break and then maybe look at a few old quiz questions? Yeah, okay, so let's take a break for a minute and then be back afterwards.
This was a question that's evident to other people, so I didn't ask it. But like, I still am not clear why it's faster for I can't just search for hash as opposed to searching for term. Like, it's not clear to me because it still has a memory address. So why is it looking at a longer hash number is faster somehow than finding a single object in the list?
Finding a single object in the, okay, so suppose that in a, oh. Okay. Okay, let's, yeah. All right, so let's see what's coming up in your, the kind of questions that come up in the quiz next week. Next week? Yeah, week 3, no. Okay, yeah, sorry about that. Okay, all right. Okay, so let me do this. All right, so true or false? If I have to search inside a list of 1,000 items, is it better to first sort the list and then use binary search rather than just using linear search? Think about it for a minute and then. Okay, so what's the answer? It's kind of not a like clear-cut answer, I would say. and this is just to discuss this point here. This wouldn't be the type of question that you will see on the quiz. Okay, so 1,000, it's probably worth sorting the list first and then do binary search, because binary search is super, super efficient, and sorting is only n log n. And n log n is really not really expensive. So instead of linear search, you might just as well sort first and then do binary search. It's just a couple of more steps. I think it's worth it. But it depends on the case, on the situation that you're in. You just go through all of the items to O of n, yeah. And if you sort it, it's O n log n. Okay, and O n log n is actually very, very cheap to do, because log n is just a couple more steps. Yeah. Okay, so the best sorting algorithm runs in n log n, so we've already gave away the answer. Yeah, so, okay. Yeah, the elements of a set are maintained in sorted order for fast searching. It's false. From Python version 3.7, I guess, Python retains the order of insertion inside a set, but that's not to say that you can loop over them using an index or something like that and rely on that. So it just maintains that. So you can't access those items by index. Still, you have to use the hashes or directly go to that item. But it maintains the order. Same goes for dictionaries. It maintains the order by default. Okay, searching for a key in a dictionary takes O(n) time, but searching for a value takes O(n) time. Is it true or false? True. Okay, right. Because the keys are hashed, that's O of 1. Values aren't. So if you're looking for a certain value, you still have to go through the entire dictionary and check everything. Okay. So this is something that you have to decide beforehand when you're designing an application or a technique. That what is it that you want to use as a key? What is it that you want to use as a value? Yes. Okay. Okay. So suppose that your keys are numbers between 0 to 1 million, and your values are just random strings, and somewhere in there for one value you have UBC, and you're looking for UBC. How can you find that? UBC does not correspond to the hash or to the key in any way, so you still have to check everything. Yeah. Sure. So maybe I didn't understand it correctly. So okay, so using reverse hash. So you mean that using those data, those values as keys themselves? Is that the question?
No, as a keys approach is you have the value and you want to look up the value. You first use reverse hash function to get it.
Oh, okay. This is an important thing here. You can't really go back. The hash function is kind of one way. Yeah, it's very, very complex to actually determine what was the value that generated this hash. And this is kind of related to all the topics of security and cryptography, that when you, for example, in SSH keys, when you hash something, it takes like 1 million years to brute force that back to the value that generated it. Yeah. Okay, if two Python objects have different hashes, they will end up in different buckets in the hash table. True or false? Right, it's false, because we saw that sometimes as the size of the dictionary grows or the set grows, some items will end up in the same buckets. Right.
What if we have a dictionary of lists?
You can't have a dictionary of lists. I mean, as you can't use.
Value.
Okay. So, and then you're looking for.
Looking for a value.
Okay, sure. Then you have to again go through the entire dictionary to find that list that contains that value, and then go through each list to find that value. Right? Yeah, O of n or worse, depending on what the size of the list will be. Yeah. Okay, so a couple minutes left. let's see if we can cover another question over here. Okay, suppose that you're given a list called word frequency containing all unique words and their frequencies. Okay, for all published works by William Shakespeare. The words are sorted alphabetically. For example, the list might look something like so: act 102 times, half 41 times, the 18,000 times. If you want to find the most frequently occurring word, would you use linear search or binary search? Briefly justify your answer. So think about it for a couple of seconds.
I would use linear search because binary search requires things to be sorted numerically, but you're not really, these are sorted alphabetically, but not numerically.
Precisely. Yeah, that's right. This is sorted alphabetically, but you want to find the most frequent word, which requires you to have a sorted list based on frequencies. So it wouldn't work. You just, again, similar to the dictionary situation. You have to do linear search because it's over the values we're looking for are the second items by which the list is not sorted. Okay, so I think I think it's enough for today's lecture. Thank you so much, and I'll see you in the lab today.